sorry, Doc, can you move here? I want to use like this. So I will keep all these things here, and then we can go over one example on this side. See what happens. So example, this is our textbook, BMW, the initial of the last name of the three authors, and on page 107. Okay, so from one radar site, we have the following observations. The rho equal to 0.4 and DU and AZ equal to 90 degrees and elevations equal to 30 degrees. And rho dot equal to 0 and AZ dot equal to 10 radius per TU, and E elevations equal to 5 radius per TU. Okay, so one radar site at 0600 GST has observed, has measured the following information. And this radar site has the longitude 60 degrees west. Sorry, the longitude 150 degrees west, the latitude 60 degrees north. Okay? So we want to calculate is R and V of the observed sat at the time of observations. Trust me, once you have this technique, if you are able to do these calculations, you should be able to predict the satellites. So, which means, I would say if any soldiers or any, I wouldn't say that one, but some terrorists in Mid East, they have this knowledge. They can predict some spy satellites when they have to hide there. If you have R&D, you can do that one. And in our chapter 4, chapter 5, our focus will be on this one, prediction, and also determine the weather rule. If we have the missile to be launched and to strike something, then we will be able to do it in our preliminary calculations. At the end of this semester, you will go away with this knowledge. Trust me. Okay, and so with this one, then we determine is rho in SEZ. And again, this is our the spherical coordinate systems. So if you still remember our coordinate system, say this is the this is our AZ and this is the satellite. And right now I want to highlight the three components. So this is satellite and this is okay, so this is a component in S directions, this is a component in Z direction, this is a component in Z directions. And so from here we have azimuth angle is measured from the North Pole, so that is AZ. And elevations angle, that is the EL. And what is rho? Rho is this one here. Okay, so by looking at this graph, this one, basically you can see this one is equal. Again, this is on the lecture notes a couple days ago, and if you can flip over, you should be able to see this is rho sine theta, sine EL, right? And so this one is rho sine, rho cosine EL, and then in sine AZ, and this one is rho cosine EL and cosine AZ. Okay, so keep those kind of calculations. So here we have is 0.346 and 0.2, and unit is in BU. Okay, so now we can determine this one. So this one, I would say refer to the notes and last week. And because it's a long writing, we can always refer to that. Is very, very straightforward. And this one involves, I think, if you remember, if you can flip over, I think 3 lines, very long lines of the calculations. So let me skip out that part, and that result will be equal to 3.46 minus 1.73 du. Okay, so from those things, we can proceed calculation, and that is in SED. Okay, so now our step 1, follow up this kind of step 2, follow up our calculations. So here we have R, and so therefore R is easy by following up, because right now our R is only to, our S easy only the green line, so we need to add it up the R. So therefore this one is rho S easy plus R, that is the, this is the radius. R. Okay, so R dot is the positions of radar site. Okay. So right now we put into here is 0.346.2 du, and plus R, if R we express in SED. So look at here, if we express R in SED system, so that should be 0, 0, 1, because the Earth's radius is 1 du, right? Can you see it? So this is our R in SED. Look at the map here. Look in the drawing here. The R is the pointing to Z direction, and here we're taking du as a unit. So basically, this is the 1. Good. Okay. So that is 0.346, 1.2, and du. Okay, so now we're going to determine theta and determine L. So now we come to the point, what is L? L, by looking at this graph here, and that basically is our elevations of the radar site. So L equal to elevation of the radar site is how much? Elevation is 30 degrees, so this is 30 degrees. And now come to theta. Theta is a little bit theta is determined by this, and let me translate the information. I think this will be the first time for you what is GST. 0600 GST, and that means that is the 6 a.m. I wouldn't say that one. And that means basically it's saying right now the Greenwich is here. And I'm telling this angle here is 0600 GST. So GST 06 is simply this angle here. And that basically is the 6 a.m. Measures reference to the y-axis. And for Earth, once 360 degrees is 24 hours. And for 6 hours, basically, this one is 24 hours. And rotating, spinning, make a complete cycle. And here we only proceed at the Greenwich side only 6 hours. So basically this one is 90 degrees. So therefore, at that moment, the Greenwich locate is 90 degrees just past the y-axis. Okay? So GST, and sometimes convert compared to GST, sometimes you will see is LST. LST is a local sidereal time. This is Greenwich sidereal time. For the local, that means, for example, here, say, Fairbanks LST. So that means simply tell this Fairbanks LST is from here to there. Okay. So from here we can tell is this one, so that is the side talking. So right now we know the longitude. The longitude of Fairbanks is the longitude here is 150 degrees west. So right now we simply add it up is this 90 degrees, and that is the Greenwich current position with respect to y-axis. And in addition to whatever the relative locations, so here we always measure east positive and west negative. So here we take the minus of the 150 degrees, and this one basically gives us the theta as we shown there. Try to get used to this kind of the concept, and that's a way to uniquely tell your positions for an alien in space. They don't live on the Earth time. They live on the universal Julian time, Zulu time. I think the American is so great because he works on the global issue, global affairs, and for the military to execute, perform their missions, they be better. So sometimes from movies you say Zulu time, right? And even in some scientific movies, Julian date, those ones that really is try to talk about the same time, this moment, in terms of the uniform. Okay, so get used to. So right now we have this one is minus 60 degrees. So with the two numbers, we are able to determine D. So therefore, D is can be determined. Okay, so here, therefore here we can determine D minus. Inverse, this one quickly do the calculations here and provide this number to you, 433. Okay, we need D minus, so we need the D inverse, so keep these things in mind. So right now we already have, so therefore, step 2, we simply plug into here, so XYZ in IJK. And that is our RIJK. We have obtained the first element, so that is a D inverse multiplied with R in SEZ. Okay, right now I'm applying this formula here. Okay, so basically here, this one is R ijk, and this one is R in SEZ. Okay. So the numbers, that one will give us, I can read for you, is 0.6 minus 0.346 and 1.039 in terms of the DU. Okay, if that be too low, stand up to look at it here. Yes?
And so you found the D matrix just like plugging L and
Yeah,
and theta into
yeah,
that, right?
yeah. So that needs a little bit of time.
Yeah, no.
Okay.
I just wanted to make sure.
Good, good. So step 3, we determine the V ijk. So simply plugging into this equation here, and ijk will be equal to omega of the Earth multiplied with R plus the rho ijk dot. Okay. So here the omega I would say this is ijk. This is in terms of the ijk. So everything is in ijk. I want to emphasize. So this one is in ijk. The Earth rotations, and this one, rotation speed of the Earth, we can find from the appendix, and let me cover that one for you. That is 0.588 du/tu. So this is the rotation speed of the Earth, and that is in ijk, measured in ijk corner systems. And R ijk, and we found already. And rho dot ijk basically is a inverse and times rho in SEZ. Okay. And this one I can give you this number, that is 1.067 minus 3.848 minus 0.232 du. So therefore, with all the information ready, and we have V ijk, and let me give you the result directly. So that is 1.0874 minus 3. Okay, so that are our results here. Where is R? So this is our R. We found R and we found V. So with the two things, you simply repeat our exercise, homework exercise this week we just do today. And you can determine the orbital element. The numbers here are not so clean, which have a lot of the numbers after the digit point, but with the program you can do it. Okay, so from here, this is the orbital element. And if the observation is accurate, one side note, at this moment, we have R and V, we can determine orbital elements. If that is the same orbit you observe, 1 hour later, we will observe another set of the data here. You repeat the calculation, getting R and V. And doing the R and V, you can get another set of the orbital elements. Again, if the two data you observe 1 hour in space, if they are the same with the same satellites, then you should expect that the orbital elements must be the same. Otherwise, you spy on the different objects in space. And that will provide another checkpoint for the calculation, see if your calculation is correct or not. Okay. So today we kind of gone through, this is a very tedious, not very tedious calculations, and I would say here we list out all the native calculation and with the formulas. And I would say if anyone have your phone, then you can take the pictures, and then this will be a good one. If you have, anyone take the good image? Are you able to put the one into a single shot and email that to me? Or you need a two shot? Or I don't know how to. I have a phone, but I barely play with it. I really want to. I don't know how to do it. Thank you. Okay, that is for today. Thank you.